universe has a soundtrack. It hums, it chirps, it roars with cosmic violence. And for the first time in human history, we're finally tuning in. Over a century ago, in 1916, Albert Einstein reimagined the cosmos. His theory of general relativity described gravity not as a force pulling objects together, but as a curvature of spacetime itself, a flexible four-dimensional fabric. He predicted that when colossal objects accelerate through this fabric, they should create waves, sending ripples outward at the speed of light. These were not waves of light or sound, but waves in the very structure of reality. For nearly 100 years, this idea remained one of the most profound and unproven predictions in all of physics. These gravitational waves, the faint echoes of cosmic cataclysms, were thought to be so unbelievably weak that detecting them would be impossible. A theoretical ghost we could never hope to catch. The universe, it seemed, would keep its deepest secrets. What exactly are these cosmic ripples? Imagine spacetime as a vast cosmic trampoline. Now place a bowling ball in the center. It creates a dip, a curve in the fabric. This is how massive objects like stars and planets warp spacetime, creating the effect we experience as gravity. But what happens when two bowling balls, or better yet, two black holes spiral toward each other and collide? Their immense mass and incredible speed don't just create a static dip, they violently churn the fabric of spacetime. This disturbance doesn't stay put, propagates outward, like the ripples from a stone thrown into a still pond. These are gravitational waves. They are ripples of pure gravity, stretching and squeezing everything in their path, from distant galaxies to the atoms in your own body. They carry with them the untold stories of the universe's most extreme and energetic events. Cosmic messenger service, delivering news from the dark heart of the cosmos. The challenge was that, by the time these waves travel billions of light years to reach us, their effect is almost infinitesimally small, a whisper from a distant storm. Then, on September 14, 2015, everything changed. In the quiet data streams of two massive detectors, one in Louisiana and one in Washington state, a signal appeared, lasting less than a second, but it was unmistakable. Scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, had captured the echo of a truly monumental event. Far across the universe, 1.3 billion years ago, two black holes, each about 30 times the mass of our Sun, had been locked in a death spiral. As they spun faster and faster, they unleashed a storm of gravitational waves, culminating in a final, violent merger that forged a single, larger black hole. In the last fraction of a second, this collision converted 3 times the mass of our Sun directly into gravitational wave energy, briefly outshining all the stars in the observable universe combined. When that faint, ancient ripple finally washed over Earth, it was detected. Humanity had, for the first time, directly heard the sound of two black holes colliding. Einstein was right. A new window to the universe had been thrown wide open. Detecting this whisper required an instrument of almost unbelievable precision. The LIGO and Virgo observatories are monumental L-shaped machines, with 2 arms stretching for several kilometers. Inside these arms, a powerful laser is split, with each beam traveling down a vacuum tube to a mirror at the far end. The beams reflect back and are recombined. Ordinarily, the light waves are set up to cancel each other out perfectly, so no light reaches the detector. But when a gravitational wave passes through, it alters the very fabric of space. It alternately stretches one arm of the detector while squeezing the other. This unimaginably small change in distance, a distortion far smaller than 1,000th the width of a single proton, is just enough to knock the laser beams out of perfect alignment. A flicker of light hits the detector, carrying the precise waveform of the passing cosmic ripple. It is a feat of engineering akin to measuring the distance to the nearest star with an accuracy smaller than the width of a human hair. This incredible sensitivity allows us to build a map of the universe's most hidden and violent events, one tiny vibration at a time. This new sense, this cosmic hearing, does not replace our traditional telescopes. It beautifully complements them. For centuries, our understanding of the universe was built entirely on light, from radio waves to gamma rays. We were like astronomers who could only see, but not hear. This is what makes gravitational wave astronomy so revolutionary. grants us access to the dark universe, the parts that emit no light at all. Black hole mergers, for instance, are the ultimate stealth events. Since not even light can escape a black hole, their collisions are completely invisible to even our most powerful telescopes. But in the language of gravitational waves, they are the loudest events in the cosmos. We've gone from not knowing if binary black holes existed to having a catalog of dozens of mergers, each one a data point telling us about the lives and deaths of the universe's most mysterious objects. We are no longer just looking at the stage, we are hearing the backstage drama. Gravitational waves are revealing phenomena that light alone could never fully explain. When two neutron stars, the ultra-dense remnants of massive stars, collide, they create a spectacular cosmic event. Telescopes can see the brilliant flash of light, a kilonova, that results from the explosion. But gravitational waves hear the final, frantic moments of their spiral and collision. By combining both signals, a technique known as multi-messenger astronomy, we can piece together a complete picture. We saw this in 2017, when LIGO and Virgo detected the merger of two neutron stars, and observatories around the world scrambled to pinpoint the light from the same event. These joint observations confirmed that such collisions are cosmic forges, creating a significant portion of the universe's heavy elements, like gold and platinum. The very gold in your jewelry was likely born in the cataclysmic crash of two neutron stars, an event we can now both see and hear across the cosmos. We are decoding the origin story of the elements themselves, and this is just the beginning. The discoveries made by LIGO and Virgo have ignited a new era of cosmic exploration. The next generation of observatories promises to expand our senses even further. Ground-based detectors are becoming more sensitive, promising a near-constant stream of detections. But the true frontier lies in space. The Laser Interferometer Space Antenna, or LISA, is a planned ESA NASA mission that will consist of 3 spacecraft flying in formation millions of kilometers apart. This enormous scale will make LISA sensitive to much lower frequency gravitational waves, a different part of the cosmic soundtrack. It will be able to detect the gentle hum of supermassive black holes merging at the centers of galaxies, the quiet spirals of white dwarf binaries throughout our own Milky Way, and perhaps even the faint primordial rumble left over from the Big Bang itself. With these future instruments, we will be able to map the universe's evolution in an entirely new way. When we combine the light from a telescope with the ripples in spacetime from a detector, it's like watching a cosmic symphony with the score in hand. We are witnessing the universe's most dramatic moments with an unprecedented level of detail, gaining profound insights into the fundamental laws of physics, the life cycle of stars, the creation of matter, and the grand unfolding story of the cosmos itself.
Stay curious.